great pleasure to introduce today's speaker, Marcin Lis from Vienna, and Marcin will tell us about an elementary proof of phase transition in the planar XY model. And let me say that, as usual, the seminar will be recorded and made available on our YouTube channel. And I now leave the floor to Marcin. We're looking forward to your talk.
Thank you, Marcelo, and thank you, Daniel, for the invitation. It's a great pleasure to be able to present this work today here. So it's a joint work with my PhD student in Vienna, Diederik van Engelenburg. And for the outline of the talk, I will first start by introducing the XY model. So it is a model of statistical mechanics, a spin model where the spins lie on the unit circle in the complex plane, so with a continuous symmetry. And I will try to explain a special type of phase transition that it undergoes in 2 dimensions, the so-called Berezinskii-Kosterlitz-Thouless phase transition that was first rigorously established by Fröhlich and Spencer in a famous paper from '81. So basically, at this point, I will stop talking about continuous objects, and I will move to talking about some discrete statistical mechanics models which underline the XY model. So first, I will, in the second part, introduce the notion of currents and the associated height function. So it will be a random integer-valued surface in 2 dimensions. I will talk about its FKG properties, which are basically positive association properties. And I will mention a beautiful recent result of Pete Lammers about delocalization of this height function. So this will be an external input for our proof. After that, I will go on to introducing a loop representation of the model. So it will be a random collection of loops, which carries both information about the height function, but also about the spin model. So after I've introduced these 2 objects, I will be able to present you a new proof of this BKT phase transition, and it will be basically in 2 steps. The first step will be to show that delocalization, which we will have by Pete's result, implies that there is no exponential decay of correlations in the model. And then the second part is using more classical inequalities to show that no exponential decay actually implies a power law lower bound on the 2-point function. Yes, and please, if something is not clear, ask a question. So what is the XY model? So we start with a finite graph G, and to each vertex V, we associate a spin sigma, which lives in the unit circle in the complex plane. And we put a probability measure on the space of all such assignments of spins, so spin configurations. We call this measure mu, and it's given by this following formula. So we have a reference measure. So for each vertex, we put a uniform reference independent measure, probability measure on the unit circle. And then we bias it by this Gibbs-Boltzmann factor, which is an exponential of the Hamiltonian. And the Hamiltonian is given by the following sum. So we sum over all edges in our graph. And then there is a coupling constant J, which will be positive. And in most of the cases, it's just equal to 1 in our discussion. And then we have sigma V, sigma bar V, where bar is the complex conjugate. And the second term is the conjugate, the complex conjugate of that. So that's the Hamiltonian. And then we have a partition function, which renormalizes the measure, the probability measure. So if you look at you can parameterize spins on the unit circle by the angle that they make with the x-axis, for example. So you can write them as e to the I theta. And then each term in this Hamiltonian, you can interpret just as the cosine and the difference of the angles at the 2 spins or at neighboring vertices. Okay, so this thing is the biggest when these 2 angles point in the same direction, and it's smallest when they point in the opposite direction. Since J is positive, the model is ferromagnetic, so it favors the spins to be aligned with each other. So I will write the sort of classical brackets for the expectation with respect to that measure, and I will also often look at infinite graphs. So for an infinite graph, I can also define this expectation operator, which is just the limit with finite graph exhausting my infinite graph. And this limit exists by some classical correlation inequalities like Ginebra inequality. So this is the model with free boundary conditions. And I'll also at some point mention a model with boundary conditions which are fixed to be equal to spin, which is equal to 1 pointing to the right in the complex plane. So then I will put a 1 on top of this notation. And since our theorem works actually for any periodic planar lattice, but I will basically explain it only in the case of the square lattice. So here we have, okay, so this didn't refresh, I see. Okay. So there is some problem with refreshing. Okay, I will try to, sorry, I will stop my share and share via cable. I think this is sometimes, this is much more reliable, even though you will see all my, the whole interface. Okay, so here you have 3 realizations of the system. On the left, it's at low temperature, so the spins tend to be aligned with each other. And on the right, we have high temperature, where we have basically a disordered system. And in between, there is something also in between. So a question that one can ask is there a phase transition in this model in 2 dimensions? So for example, you can ask, is this quantity, so I would like to look at the expected value of the spin at 0, say with 1 + 1 boundary conditions on the whole Z2 square lattice. And I would like to understand what the value of this thing is. So one could expect that, say, at low temperatures, the spin in the middle will somehow remember the boundary conditions also in the infinite volume limit. So one could ask, is this positive at low temperatures? Like, for example, for discrete spin models. So the answer is that this is always 0. So the spin in the middle never remembers, at least in this sense, the boundary conditions at any finite temperature. And the reason for that behavior is, for example, the following picture. So here we have a big box with +1 boundary conditions. So all the spins on the boundary point to the right. And in this configuration, we slowly change the direction of the spins when going inside the box, so that in the middle of the box, the spin actually points in the opposite direction. And one can see on the right, one can compute the energy of this configuration. And the energy of this configuration will be of order 1 over the logarithm of the size of the system. So it will vanish when the box grows to infinity. And because of that, so we will see configurations like that appearing in the system because they have 0 energy in the limit. So this is the content of the famous theorem of Mermin and Wagner, who said that there is no spontaneous symmetry breaking at any finite temperature in the model. And this holds for any model with continuous symmetry, actually. So before I go on, I want to make a few comments. So this is not true already in dimension 3, by also a famous paper of Fröhlich, Simon, and Spencer, who used the infrared bound and reflection positivity to show that at low temperatures, in higher dimensions, the spin in the middle of the box actually remembers the boundary conditions. So there is magnetization at low temperature. And also one can look at something which is a approximation of the, say, of the XY model, where we have a finite number of values of the spin on the unit circle. Okay, so the simplest case is the Ising model, where we have only possible 2 values, and then we have magnetization at small temperatures, but we can also look at more and more possible values of spins. And the theorem here is that it doesn't matter what the number of spins is, since the model is discrete, there is a minimal energetic price that you have to always pay for changing the spin. So if you make the temperature low enough, the price will be very high. And because of that, by some Pios type argument, and the spin in the middle of the box will actually remember the boundary conditions at low temperatures. So this theorem only holds in 2 dimensions for the XY model with a continuous symmetry. So one way to look at it is also the behavior of the 2-point function, which will be more important for us in this talk. So a theorem of McBrien and Spencer from 77 says that at any temperature, the 2-point function, so the expected value of the product of a spin with a spin conjugate. So if there was no conjugate here, then this would be simply 0. So it would be a trivial correlation. So we look at this 2-point function, and then this has a power law decay. There is an upper bound which gives you a power law decay of this object in terms of the distance between these two spins. And this holds at any temperature. On the other hand, using some classical, say, high temperature expansions, one can always prove that at high temperature, the 2-point function decays exponentially fast. So the question here is that, is the exponential decay always true, or is there maybe something interesting happening in the system? Is there some phase transition which is not the spontaneous symmetry breaking type of phase transition? So the answer is that there is a phase transition, and apparently still in the 70s, people in physics were not sure about the answer to this question. So the idea here is to somehow look at the model from a different point of view. So here we have a nice picture of a configuration of the system, and we can try to look at it from a more geometric point of view. And we quickly realize that there are these points in the system, or faces actually. So this is on a small mesh size square lattice. There are these faces of the system where if you go around that face, and the angles of the spins, they actually make a full turn, 2 pi, either in one direction or in the other one. So it's 2 pi or minus 2 pi. So these can be thought of as topological excitations of the system. We call them vortices and anti-vortices depending on the direction of rotation. And it was realized by Kosterlitz and Thouless and also Berezinskii that you can try to describe the model in terms of these topological excitations. And what they realized is that these excitations, they always, it's energetically favorable for them to be close to each other, and namely a vortex wants to be close to an anti-vortex. So the interaction is actually of logarithmic strength in the distance. So they decided that there should be a phase transition in the sense that there should be a temperature, if you increase the temperature, at which the sort of entropy wins over this energetic cost of vortices being bound to anti-vortices. And at this temperature, we should see the unbinding of these vortices. So they should form a freely spaced, somehow plasma of vortices and anti-vortices. So that was their insight. And we would like to think about this phase transition in terms of correlation functions, or at least for this talk, in terms of the 2-point function. So there is a heuristic that you can try to implement, which tells you that at low temperatures, the 2-point function should decay polynomially fast. So we have an upper bound, but the heuristic says that it should at least be, that it should also be a lower bound. So what is the heuristic? So for example, you can say that, okay, at low temperatures, these spins, so there will be, first of all, very few vortices and anti-vortices, and then they will be close to each other, okay? So since also the angles will be, the angles at neighboring vertices will be close to each other, we can then try to approximate this Hamiltonian that we have. You remember we have our Hamiltonian is 1 over beta times cosine theta vertex and theta neighboring vertex. So what you can say is that at low temperature or high beta, these two numbers inside will be close to each other very often. So you can try to approximate this cosine by its Taylor expansion of degree 2. So you can just write that this is approximately the same as theta v minus theta v prime squared. So this is all in the exponential in my measure. So basically the first term should be just a constant, so it doesn't influence the probability measure. And then the second term is just a Gaussian interaction. So it is a Gaussian interaction, but our angles they are not defined on the full line, but they are, say, from 0 to 2 pi. But then you can say that since these vortices and anti-vortices will be close to each other, actually, you can think of the fact that the increments of the angles will actually give you, when you integrate them, they will give you a well-defined height function or a real-valued field, which will be defined almost everywhere because the vortices will be bound to anti-vortices. So you can think of actually theta to be H, where H is a real-valued field. So at low temperature, there should be some real-valued field which underlies the system with a Gaussian distribution, and this is just a discrete Gaussian free field. So if you think that this is a correct intuition, then you go back to your model and then you say you would like to see what is the expected value of the spin at the origin with +1 boundary conditions in a square box of big size n, then this should just be equal approximately to the expected value of the imaginary exponential of your discrete Gaussian free field in the same box. And since this is a Gaussian random variable and we know its variance, so variance of such a Gaussian field is just is given by the Green's function of random walk in the box. So this is equal approximately 1 over 2 beta pi log of the size of the system. And then here we see that this is basically this is a characteristic function of a Gaussian distribution. So this expectation is just e to the minus 1/2 of variance of this object. So it's e to the minus 1/2 of this quantity, which is a logarithm. So in total, we get that the behavior of the spin or the expected value of the spin should be polynomial in the size of the box. So at low temperatures, the expected value of the spin inside the box should decay polynomially to 0 when the box goes to infinity. And it can be proved that at high temperatures, it decays exponentially. So there should be a phase transition of this type. And this was, okay, for the 2-point function, this was exactly proved by Fröhlich and Spencer in 1981. So they proved that there exists a temperature such that if you go below that temperature, the 2-point function is bounded from below by a power law in the distance between the 2 points. And what they actually proved is something more here. They proved that this exponent that you get, it actually decreases to 0 when the temperature goes to 0. So the 2-point function decays to 0 slower and slower when you decrease the temperature, which is obviously intuitively clear. Also in that paper, other models were studied. So for example, there were results about the Villain model, which is a version of the XY model with a different Hamiltonian, which is useful in some context. Also, Coulomb results about the Coulomb gas were obtained, and the Q-state clock model that I mentioned. So there's many results in this paper, and it's also quite technically involved. So the purpose of this talk is to present a proof which is different of a result which is similar. Okay, it's slightly different, but it's similar in nature, and our result holds. So our proof is only about the XY model. So what we can prove is basically the same result, and there are two differences. So the first difference is that at low temperatures, our lower bound, so we have a polynomial lower bound, but it doesn't improve with the temperature going to 0. So it just always, the exponent is always equal to 1 with an explicit constant. And the other difference is that we actually pinpoint a single temperature or a single inverse temperature at which the transition occurs. So this is a type of sharpness of the result. So we can say that for higher temperatures, strictly higher temperatures, there is exponential decay of the 2-point function, and for lower temperatures or equal, this statement also holds at the critical temperature. We have a power law decay of the 2-point functions. So this is the statement of the result. Are there any questions at this point?
Do you know anything about the constant C? I mean, how it goes to 0 as beta goes to beta C?
So this we don't know. I mean, from the result, it follows that it goes to 0, but we don't know how fast. But I think there are theoretical predictions, and this should be related somehow to the phase transition also of the random cluster model at the where you vary the Q parameter actually, and there is a phase transition at Q equals 4, and there is some theoretical prediction that these two correlation lengths, they should behave the same way when you approach the critical point. But I don't remember.
Another question. So what's the prediction for the sharp exponent at beta C?
So this I also am not sure. I think I heard that 1/4 should be already okay. It's at least 1/4. So I mean, obviously our result is not optimal for sure. The exponent here we get from an application of the somehow Simon-Leib type inequality, and from that you get exponent 1. But I think you should be able to go down to at least 1/4. I think, from what I remember.
Okay, thanks.
Okay, so I will go on to define these discrete models that I will talk about. So first of all, we have the same graph now, and I endow it also with a set of directed edges. So each edge gets 2 copies oriented in both ways, as in this picture of mine. And then I call a current. It's an integer valued function on these directed edges. So that's just the definition of a current. And then I say that the current is sourceless if, I say that the current is sourceless at this vertex if the number of incoming arrows, or the number of current, the value of current incoming to the vertex is the same as the current outgoing of the vertex, as it is the case in the picture. So these are sourceless currents. And then I define a weight on them, a statistical weight. So just a product over all these directed edges. And then there is a factor, there are these exponential factors, 1/n factorial. Here, this is a directed edge with this curly bracket. And then this beta over 2 to the power of the value of the current. And then the observation here is simple, that if you just sum over all these sourceless currents, this is actually this partition function that I mentioned before. And you can see that these terms just come from the expansion of this whole exponential of the Hamiltonian in a power series in beta for every edge. And then we have to integrate that against the reference measure on the spins, which are independent uniform spins on the vertices. So this gives you the sourceless condition. So the sourceless condition comes from the fact that the integral of sigma to any power n, d sigma, where d sigma is the uniform measure on the circle, that this is equal to the indicator function that n is actually equal to 0. So this integral vanishes only always unless n is equal to 0. And then if you, for example, note the easing currents, then the difference is that for easing, the reference measure is just uniform on ±1 spins, and then you get an indicator function that n is an even number here, so it's 0 modulo 2. And these easing currents are objects like that, but with the condition that they are sourceless modulo 2. And for the XY model, they are actually sourceless truly. So the sum is 0. It's not only 0 modulo 2, but it's 0. So these are currents. And then you can think of a probability measure on these currents, which is induced from these weights. So by the way, I'm not reading the chat. So if there's any questions in the chat, I see that there is something.
So far, no questions. We're just sharing your slides. Yeah.
Okay. So what is a height function associated to a source's current? So you assign to each face of your graph a value, which is an integer. And so the faces of your graph, they can be connected by edges, and this will form a dual graph in red here in this picture. And the rule to define this height function is that, say, if I put value 0 here, then I look at the current gives me the gradient between two faces. So here I have 0 edges to the right and 2 to the left. So I say that the current increases by 2, which is 2 minus 0. And then it decreases by 1, which is 2 minus 3. And then it decreases by 1 again, which is 1 minus 2. And then it doesn't change, which is 5 minus 5. And this gives the current gives you a gradient, and the fact that it's sourceless gives you actually a well-defined height function. So if you go around a square like that, you will come back to the same value. And then we put the value of the height function at the external face of the graph to be 0. So once you fix the value to be 0 outside, it is a well-defined height function. So this model is the planar dual model of the XY model in some sense. And we denote by this P the probability measure on these currents and also on the height function. So if you work with gradient models or height function models, then you would like to probably put this height function into the Gibbs sort of formalism. So you can rewrite this probability measure in terms of the expectation, and then you have a sum over every edge in the graph of the potential function of the gradient of the height function between these two faces. So you can define this potential from the definition of currents, and then if you look at it, what it gives you is that this potential is just minus logarithm of what's called the modified Bessel function of the first type. So just to maybe, so if you have these two edges oriented in two ways and you look at the gradient between two faces, then there is an infinite number of ways you can achieve this gradient, because the gradient is the number on one edge minus the number of the other edge. And if you sum all these possibilities, so here is the sum over all these possibilities, and each contributes a weight coming from the random current model. And this is just a definition of a Bessel function. So these Bessel functions are obviously classical objects and well studied. So for example, one inequality tells you that they satisfy this Turan type inequality, which you can interpret in terms of our potential as it being convex on the integers. So it's a height function, it's a gradient model, discrete integer valued gradient model with the potential which is convex on the integers. So this puts the model into a family of models that have been studied quite extensively in the literature, for example, in the PhD thesis of Scott Sheffield. And then it is also known that if you have this convexity of the potential, then your height function is FKG, which means that it is positively associated. So so if you compute the expectation of any, okay, so intuitively it means that if you know that the height function has a high value somewhere, if you condition on that information, it becomes more likely that it's also high value somewhere else. So this is one thing that we know. But it has been it became obvious in recent years that it's very useful to have a different property, which we call absolute value FKG for the height function, which is stated in this proposition. And this intuitively tells you that if you know that the absolute value or the modulus of the height function is high at some point, then it should also be, then this increases the probability of it being high at some different points. And it can be stated in this classical FKG formulation like here. So I just want to say 2 words about the proof of this fact, which is crucial for our proof. So first of all, we use a condition of Lammers and Ott from a recent paper, which says that if your gradient, discrete gradient, if you compute this discrete second derivative of it, and it is non-increasing on a function on the integers, then your height function is absolute value FKG. So this gives you some inequality on the Bessel functions. So we tried to use this lemma and to prove that the height function is absolute value fkg, but we could only prove it for very small values of beta. Okay, at some point we could prove it for beta smaller or equal than 1. And we are stuck. And at this point, we are not sure even if we should expect that it's absolute value fkg for all beta. And this was the first step that we had to check for our proof to work. So then we realized that you can overcome this problem by a very simple trick, which does the deed somehow, but you don't do really much. Okay, so the point is that once you have this absolute value fkg property for beta smaller or equal than 1, then what you can do in your graph, you can replace every edge by n edges, where you put interaction constant beta over n. So this is just a trivial modification of your graph, which doesn't change the distribution of the spins. In any somehow statistical mechanics model with this type of Hamiltonian, you can just make these dummy edges which have an effective potential which is smaller. They add up to not the potential, but the interaction strength. So if you look at it from the dual point of view, this means that on the dual graph, you actually introduce, so before there was an edge on the dual graph between two faces, but now there is a bunch of vertices on the dual graph in between of your 2 points which are fixed from the original dual graph. So somehow we have a height function now which is defined on points inside the edges of my original dual graph. And now, since I know that the temperature here is smaller or equal than 1, I know that it's absolute value fkg. But then I just say, okay, I mean, it's absolute value fkg actually on all these black points. So it's in particular absolute value fkg on these points, which are the original dual lattice. So that's the whole argument. And somehow this tells you that you can extend this height function naturally inside the edges. And this property is very nice. So the main point that people always say that you should study the V-line model instead of the XY model because the dual height function is nicer for the V-line model because it's the integer valued GFF. But for example, this integer valued GFF, it doesn't have this property as far as I know. So here we use somehow this identity is the same as saying that the sum of two independent Poisson random variables is again a Poisson random variable. And somehow it plays a role here, and this is the whole argument. So we check this lemma for small values of beta, and then we say, okay, but this is enough. So in particular, we know that we don't still know if this lemma or if this condition is true for higher values of beta, but we know that the height function is absolute value fkg. So this is not an equivalence. This is a stronger condition.
Sorry,
okay.
Can I ask you just a quick question? So the addition of these extra bonds, this is, I mean, somehow you're saying that your original model is equivalent to one where you have a larger number of bonds, or I mean, so how do you introduce these extra connections?
So in the Hamiltonian, you just write beta as beta over n plus beta over n plus beta over n, and so on. This is the same model. You didn't do anything.
Okay.
And you rewrite the Hamiltonian so that you interpret these terms as new edges in your graph. So effectively, you decreased your temperature. Somehow, our argument for this condition, it doesn't depend on the structure of the graph. It's just an inequality for Bessel functions. So now I just change the structure of my graph, and on that graph, my model has a different temperature. And we use that property.
Okay, thanks.
And this is, for example, I don't think you can do it for the V-line model. Okay, so why is this an important property? Is because if you have this absolute value fkg for the absolute value of the height function, you know now that 0 is the smallest element of natural numbers. So if you have 0 boundary conditions on your graph, on your height function to begin with, so you have a box, and then you have 0 boundary conditions for your height function, then if you increase the box, it means that you push the 0 boundary conditions away. So your model is actually stochastically increasing by this absolute value FKG property. And this gives you directly this dichotomy property, which says that there's two possible scenarios. So if you look at the expected value of the height function in absolute value in the center of the box, and now you start growing your box to infinity, so this thing will actually increase this expectation by this stochastic monotonicity. So it's an increasing sequence. So there's two scenarios. Either it just stops at some point, so it's bounded, or it increases to infinity. So the first case is when it's bounded, we call it's the localized phase for the height function. And then also the model somehow, the whole distribution of the model converges to an infinite volume limit height function. And the second case is when the fluctuations of the height function in the center of the box, they are unbounded. So the model delocalizes, and in particular, there is no translation invariant Gibbs measures for the height function. So in the second case, in particular, we have that the supremum of the expected value of the height function in the middle of the box diverges. So, this is somehow these are two possible phases for the height function, which is a dual model of the spin model. So it is expected that there should be a phase transition, and it should happen at the same point for both models. And the point of our argument is that, okay, by a result of Pete that I will mention now, we know that at low temperatures, we are actually in the second case of this scenario, where this expected value diverges. And then our argument will translate that into the power law decay of spin correlations. So what Pete Lammers proved recently, I mean, he has a very nice result, which is very strong. It works for a very broad family of potentials, which are convex and which are excited. So the excitedness is just a condition about the two values of the potential at 0 and 1. So you look at the two first values of the potential, and they should satisfy some inequality. And for us, it's an inequality for Bessel functions again, and we can check that it's true for beta high or for low temperature. It can be easily checked. So this is a very general property of his result, but there is a point which is not so general in his paper, is that he requires the dual graph to be of degree maximal 3, which means that the primal graph is a triangulation. Okay, and this is a crucial point for him, but we will remove this condition in our argument, so this is not really that important. So you can think of this as Pete giving us the result that the height function also on the square lattice, say, delocalizes at low temperature. So we have this dual model, which is a height function model. By Pete's result, there is a finite temperature where it delocalizes. And what we do with it is we want to try to translate it, make a statement about the two-point spin correlation, not the height function. So for that, we define a loop model. So what is this loop model? So you can sample it in the following way. So first, I sample a multigraph of my graph, which is Eulerian, which means that each edge, okay, so the original graph is just one cell of the square lattice, say, and now I sample a multigraph, so each edge can be replaced by multiple edges, but with the property that there is an even number of edges around every vertex, as here. And okay, there is a weight assigned to each such picture, and here this is just the number of Eulerian orientations of this guy, meaning that it's the number of assignments of arrows to these edges in such a way that there is an equal number of arrows coming in and going out around every vertex. So there is a combinatorial factor, and there is a factor which looks like the current sort of measure for this multigraph. So I first sample this multigraph, and then I say, okay, I sample a uniform Eulerian orientation on this guy. So which means that, okay, each such picture will come with the weight which forgets about this combinatorial factor here, because I just pick one of these Eulerian orientations. So each one of them will have this remaining weight. Okay, and I chose to draw one of them here. And if you just do the computation with, say, the Newton symbol, it's easy to see that already at this stage, we can recover the current underlying the XY model. So how do you recover the current? Is that you count for each edge the number of arrows which go in one direction, and you assign that number to the current on the oriented edge of the original graph. Okay, so here, so if this is, say, V, and this is V prime, then the current, okay, at V prime V, so the edge oriented towards V, will be equal to 2, and the opposite guy will be equal to 1. And if you do that, so it's a projection from this structure, which has this object which has more structure into just currents. From these two formulas that we have, from the definition of currents and the definition of this measure, you can easily see that this object already has the distribution of the current. So at this point, we already sampled the current as well, but this is not the end. So what we want to do is we want to make it into a loop configuration, which is that at every vertex, we actually connect these incoming arrows with the outgoing arrows, and we do it in a uniform way and independent for any two vertices. Okay, so this will, in sort of statistical mechanics weights terms, will be equivalent to assigning to each of such loop configurations an additional multiplicative weight, which is just 1 over the degree of each vertex over 2 factorial. This is the number of permutations of these arrows. There is degree over 2 arrows which are incoming and the degree over 2 arrows which are outgoing. And there is, okay, a factorial number of ways that you can connect them up into a loop configuration. And the corresponding picture we call a loop configuration. And this sampling procedure produces a random loop configuration, which again, if you just project down, you forget about the connections and vertices, you project down on currents, it contains all information about currents. So in particular, it also contains all information about the height function. So if I count these arrows going from right to left and from left to right, then this will give me an increment of the height function between two faces. So this loop configuration is actually coupled explicitly exactly with the height function. And if you think about, okay, so this is the result. Okay, so the partition function is just a partition function of loop configurations. That's clear. And then there is an interpretation of this height function as a winding field of all these loops. So why do we call this a winding field? So if you look at the face in your graph, then each loop contributes some factor to the height function, and the factor, okay, it's an integer, and the integer is the winding number of the loop. So this loop will contribute, say, value 2 to the height function at this face. But if you have a loop which goes, say, it goes around, but then it backtracks, or it goes around, and then it goes around in the other direction, then the contribution of this loop to the height function will be 0. Because the winding around that face is exactly 0. So it's the algebraic winding with signs. If you go one way, you pick up a sign, and if you go in the other way, you don't pick up a sign. So here we have this loop representation coupled to the height function. And obviously there is many classical loop representation of this spin system going back to Szymanczyk and Bridges, Fröhlich and Spencer. And this one is also, I mean, in some sense, it's the same representation, obviously, because it's the same model, but also the coupling with the height function has not been used yet, I think. And the way we define it is a bit different than classical, and then the classical representation. Okay, so this is the connection with the height function. And the last thing that I want to talk about is the important thing, which is a connection to spin correlations. So what we claim is that if you look at a 2-point function, but now for technical reasons, I take the squares of the spins, and then I will remove the squares at some point. The 2-point function, so the expected value of these squares, is actually equal to the expected value in this loop measure of this factor, which is a ratio of two things. Okay, they are related to each other. So M, A, and B is the number of paths in your loop configuration from point A to point B. Okay, so anyway, this is a fraction which is bounded away from 1/2. Okay, it's bounded by 1/2 from below and by 1 from above. So if you look at it, what you get is that this 2-point function is up to explicit constants the probability that there is a loop in your loop configuration joining 2 points. And that's the main difference of our approach here, is that we actually explicitly relate the 2-point function to a probability in this measure, and this measure does not depend on these 2 points of insertion. Usually in the classical expansions, what you end up with, you have 2 partition functions, and it's a ratio of them. And in the numerator, you have objects which have, say, one distinguished path from A to B, and then in the denominator, there is no distinguished path. So the main observation here is that in this loop representation, you can actually explicitly relate all 2-point functions to connectivity probabilities in the one fixed measure on configurations of closed loops. And it's, for example, also different if you think about the Edwards-Sokal coupling of the Ising model with the random cluster model. There, the 2-point function is the probability that you're connected in a percolation cluster. And here it's a probability that you're connected by a loop in this loop representation. So it's not a percolation event. And for percolation events, you're expected to have below percolation, you should expect exponential decay. So you have sharpness, and this somehow fits the picture of phase transition of discrete spin models. And here we have that, okay, it's a connectivity, but of something which is like a random walk. It's not a percolation event. And again, there's many formulas in the literature that are related to this, but we could not find this explicit formulation anywhere. So how do you prove this? Okay, so I don't have that much time, but all right. So first of all, you start with this approach, as I said, that is classical, is that you write this 2-point function as a ratio of 2 partition functions. So below, it's the partition function of sourceless currents, and above, I have currents which have 2 additional incoming arrows, or they have a double source at A and a double sink at B. So they have two more arrows coming in at A, or sorry, going out at A, and 2 more arrows coming in at B. Okay, and then the classical expansion that I mentioned before gives you that, okay, this 2-point function is the ratio of these 2 things. And now we would like to, so we know how to write the denominator in terms of the loop measure, in terms of collections of closed loops. So here, if we want to do that, there is some problem because we have these sources that maybe are annoying for us. Okay, so maybe I want to skip the formal definition of what these loop configurations are. Just I will tell you in a picture what we do. Okay, so you can try to sample these currents with sources at A and B. So here there is A is here and B is over there in all these 4 pictures. So at A we have 2 more arrows coming out, and at B 2 more arrows coming in. So you can sort of sample the same in the same way these diagrams with these sources. Okay, not sampling a uniform Eulerian configuration at some point, but orientation, but an orientation which has these 2 fixed sources. And then what you do is you proceed as follows, but you make these connections at vertices only at the vertices which have no sources, or they are divergence free, say. So in this case, we only do it at these 2 points. We connect these incoming arrows with the outgoing arrows in all possible ways. So now we have a collection of loops and paths which go from A to B, and there is no connections at these vertices. And this is the main sort of technical point that, okay, it looks like a triviality, but this is a point which actually makes this argument much simpler than if you tried actually to resolve all connections possible also at A and B. So what we do further is that we mark one of these paths from A to B. So we choose one of them uniformly at random. So I marked it red here. And then I reverse it, okay? I just reverse all the arrows along that path. So now I have a configuration of paths and loops, and also the property that all vertices are sourceless or divergence free. I reversed one of these paths, which means that now at A and at B, I have the same number of incoming and outgoing arrows. So the last step is just to connect these things up randomly and uniform and independently for every vertex. So I started with a current in the numerator of my two-point function, and I ended up with a loop configuration with no sources. And in this loop configuration, I am guaranteed actually that there is a path from A to B. That's the, or in this case, it's a path from B to A, but okay, there has to be also a path from A to B. And it's the red path that I've chosen. Okay, so this is just a picture. Obviously, to make it work, you have to compute the statistical weights of what you're doing. And this is just this computation that maybe I will spare it to you, but it's quite simple. You just, this factor MAB over MAB plus 1, it's just the bias that you have to make to make this computation work. And the whole point is that it is bounded away from 1/2 and 1 on the event that there is actually at least one path from A to B. And during this procedure, you transform the numerator into a statistical sum over objects of the same type as in the denominator. The sources have vanished, so you can interpret this as an expectation, and then you can interpret it actually as a probability of a connection. So at this point, we have a loop representation which is coupled to the height function exactly, and whose sort of statistical properties describe the two-point function of the model at least. So there is a chance that we can use the delocalization result about the height function to prove something about the spins. And that's the first step of our proof that I mentioned, is the argument that says that delocalization implies no exponential decay of correlations. So this already implies and that there is some sort of phase transition in the model. So what do? Okay, we fix the finite graph G and say gamma is our infinite graph, but it's Z2, say. So gamma is Z2 as usual. And now we make an observation. Okay, so we fix a phase somewhere. Okay, say this is the zero phase. And then there is a line of vertices on my square lattice, which goes through that phase. And we make this sort of obvious observation that a loop contributes to the height function. If you have a loop which contributes to the value of the height function at this phase, the zero phase, then that loop must intersect both the left and the right-hand side of this line. The loop must go through both sides. If it just goes through one side, it never contributes a winding around zero. So this is the first observation, and that is crucial here. And now we proceed as follows. So we say, okay, I have a finite graph, which is a subset of my Z2 lattice, and then I compute the expected value of the height function at the phase. So I say, okay, by decoupling with the loops, this is the same as the expectation with respect to the loop measure of the total winding of all loops around zero. And then I say, okay, I mean, this is upper bounded by the number of paths or parts of loops that go from one side of the line to the other side. Okay, I mean, if you contribute winding one turn around the zero phase, there must be an arc which goes from left to right. So just by counting these arcs, you have an upper bound on the height function. So you can rewrite this as the expected value. You sum over all points on the left and right, expected value of the number of arcs in your loops, which go from left to right. And then there is an argument which says that, okay, you can simply using Cauchy-Schwarz and some estimates on the Bessel functions, you can replace this expectation by just the probability of there being at least one path from A to B, and you put a square root because of Cauchy-Schwarz. And then by our loop representation, this is equivalent to saying that this is smaller or equal than 2 times the sum over 2-point functions with the squares in them. So we have these 2-point functions of squares to the power 1/2. And then I say, okay, using the Ginebra inequality, you can actually erase these 2's. So you can forget about the square root, and then this gives you the classical 2-point function. So this is a classical application of an inequality. And then I say, okay, I can actually replace G by gamma, because I know by Ginebra that if I increase my graph, then the correlations also increase. So all in all, what I proved here is that this sum of correlations from one point on the left to the right to the point to the right is bounded from below by the expected value of the height function in the center of the box. So now we say, okay, by Pete's result, we know actually that this diverges. There is a temperature for which this diverges. Okay, so in particular, this is an infinite sum for some temperature. And if this is an infinite sum, you immediately see that there cannot be exponential decay of 2-point functions. If your 2-point functions were decaying exponentially, such a sum would always be finite. And that's the core of the argument, and that there exists a phase transition. And to prove that you actually have polynomial decay when you don't have exponential decay, you use the what's called the Lieb-Rivasseau inequality, which is a variant of the Simon-Leib inequality for the Ising model. But since I'm already out of time, I will not tell you about this. But this is the last slide, which gives you this argument. And I also want to say that at the same point that our article appeared, there was a different article by Eisenman, Harel, Pellet, and Shapiro that I recommend, where they implement the same sort of strategy using Pete's result and to prove a phase transition in the model, which is different, which is this Villain model. So they say that, okay, because the height function for the Villain model, which is the dual height function, is actually the integer valued Gaussian free field. So it's an easier analysis. So they decided to study that model. And what they got is that there also is a phase transition in the same sense as on this slide, that at some point, these 2-point functions are not summable. But what I understand is that even though the height function for the XY model may seem a bit less natural, okay, I think it is very natural from this Markov property that we discussed. For example, for the XY model, we have these classical correlation inequalities that can be employed to get something stronger of this type, that we actually have polynomial decay and a sharpness. And I don't think this is, for the Villain model, I don't think there is classical inequalities like the Ginebra, for example. So this is the difference. And also, the model is different, but these two papers basically establish the same theorem using the same external result of Pete. And I would like to finish with this. Thank you.
Thank you very much for this very nice presentation. Any questions from the audience?
So perhaps one question: how important is it for you that the lattice is planar? Could you go beyond?
So the height function is defined only for planar graphs. So okay, I think there is a duality for maybe xy in 3 dimensions, as far as I know. But okay, I'm not an expert on this. But so the height function in general is a planar object, but we have also this loop representation, and in this paper on the archive that you can find, there is also a more elaborate loop representation for the model, which gives you some switching identities in type of the Ising model switching lemma. So and these things, they are valid on any graph and in particular in any dimension. So we hope that one may find an application of them, for example, to approach questions like continuity of phase transition for XY in higher dimensions. So I think this is a very nice tool, but okay, it's a bit less robust and more subtle than the switching lemma for the Ising model, but we are trying to apply it for this problem, for example.
Yeah, thank you.
Other questions? So, but for the non-planar, I mean, for non-planar versions of the XY, are there results about phase transition?
Yes, so there's the Fröhlich and Spencer paper, which gives you a phase transition in any dimension. So there is positive magnetization in higher dimensions. And we are actually not sure. So, for example, in these clock models that we have, if you take the Q state clock model, if Q is large, what is proved, or okay, what is expected and possibly what's proved, but maybe I don't have the knowledge, is that in 2 dimensions, you actually have 2 phase transitions from exponential decay to a phase which is extended of polynomial decay to a phase with a positive magnetization. So, okay, when we first thought about more dimensions, we are actually not sure if the question of existence of an extended phase of polynomial decay is expected or not, and it seems that it's not expected. For example, I think it's expected that there is a sharp transition from positive magnetization to exponential decay with the possible with the polynomial decay only at a single point. And for example, it's not known if at this point, if you take plus boundary conditions, if magnetization is 0 actually in the limit. So this continuity, as far as we know, is not known. And for example, it's proved for the Ising model using a switching lemma in a very nice paper of Eisenman et al. So we hope that we may apply our switching lemma to this problem. But it seems to be tricky for now.
Thanks. Questions or comments?
May I ask probably a stupid technical question?
Yes, please go ahead.
Could you go back to page 24, 25? It's a loop connectivities.
This one?
This one. The equation which has this asterisk, probably next page. This one. So this is a 4-point function, and I guess omega 2 is so 2 means that you have this. This is the number of sources, and but those 2 vertices A, B do not have to be connected by loops, right? Probably. Unless you consider truncated 4-point functions.
No, so what we say is that, okay, so I'm not certain if I understood, but okay, we have these 2 points which are somewhere in your graph,
Yeah.
A and B, and we say that this quantity is up to a constant of order 1/2, and 1 is the same as the probability in your loop configuration that actually there is a loop which goes through 2 points.
It's not possible to do. There is a loop at A and there is another loop at B, and they are not connected.
No, that's not possible here.
That's not possible.
Yeah,
If it is a truncated version,
Akira,
then
because sigma is a complex quantity. So sigma squared is something like e to the I2 theta. So it's slightly different than Ising.
So the point is that,
that's
like,
oh yeah,
in your original picture, you are certain there is two paths from A to B.
That's
and
true.
the point is that, okay, we say I just reverse one of them and I think of this as a loop. And that's the meat of the idea.
I see. Right. Yeah, thanks.
Thanks. Further comments?
Perhaps one more question. So everything is valid only in for the two component model. I mean for XY. But it looks like, I mean, the loop representation also works for higher components.
Right.
So, but at the same time, one doesn't expect a big transition. So,
right. So this is this outstanding problem, what that is called sometimes Polyakov conjecture, I guess, to prove that there is no such transition if your spin has at least three components. And this has been open, I think, since the 70s. And there it's expected that the 2-point function always decays exponentially. Yes, and you can do these loop expansions, and okay, you will. So we also don't know. We looked at it, but okay, you get a different loop expansion. You can also define a height function for these loop expansions, and it seems like you can also have a switching lemma of a similar type for the. So then it seems like these height functions that you get, they can never delocalize actually, which seems like, yeah, we don't know why this would be actually. And there's an article like from three months ago in the physics literature, which from what I can understand from physics, it's still unclear if people believe that there is a transition or not. They seem to be seeing some non-analytic thing in their graphs, but okay, I don't know. But I think most people think there is no phase transition, but I really don't understand how one could prove it now, because basically the height function cannot delocalize. Otherwise, you would have the same statement as here.
Yeah, so something very important happens, and you cannot make the connection to Pete Lammers theory anymore.
So then it's just a different. It's not the same type of height function somehow. It's not a gradient model anymore. It will have an interaction around the face, I think, most of the time, not only on the edges. And yeah, and I don't know. It's I don't understand it.
Do you expect the same dichotomy for this height function?
So
of course, there's no FKG, right?
Right. So there's no FKG for the spin model known. So I don't know. Okay. So I guess it's also maybe a wild goose chase to try to prove FKG for the height function. But once you have the absolute value FKG of the height function, this dichotomy is true. So this is just that. But probably there is no such FKG property also.
How robust do you think is this absolute value FKG? That something holds miraculously, or would you expect it to hold in?
So for example, to check that this holds for this Villain model, it's much easier. Okay, our proof is also not difficult, but it's for example, you have this property, this lemma to check this second derivative, and for the integer valued GFF, this potential is just the square function. So this second derivative is just constant, and then it's okay. It's somehow trivially satisfied, and then you have absolute value FKG. But okay, we have not tried to prove absolute value FKG for other spin models yet, if that is your question. We think that most of the loop representation and the switching lemma with reversing the path would work if you don't put like a uniform measure on a unit circle, but something different. But this absolute value FKG, which is obviously crucial for the argument, we have not tried yet.
Yeah, thank you.
Other questions?
How far is your proof from Fröhlich and Spencer's proof? I mean, they seem to prove something more in some respect.
Yes, yes.
Am I
So
correct?
right. So they prove a much stronger statement. So the only so as far as I understand, I must say I don't understand the full proof of Fröhlich and Spencer, but I think the general structure of them is they first say that they study the villain model because it's easier for practical reasons, and then they also look at the dual model, and then the dual model is the integer valued GFF, and then they prove that it delocalizes, and I think from that they get an estimate on the spin 2-point function. So in this sort of very general structure, this is the same, but the implementation is very different. So they use some multi-scale analysis and renormalization ideas and go through the Coulomb gas representation. So I'm not really an expert on that, and I don't want to say anything which will be not smart. So I think I would just.
Thank you. Is there any other question from the audience?
And then maybe another question. So you're using correlation inequalities for the XY, but they are not absolutely necessary, are they? You could still get some interesting result without using them. I mean, you definitely use them to relate the correlation function with a square with the other one, but it would still be interesting to prove a lower bound for these correlation functions with the squares.
I guess so, but somehow we also use the Ginebra to say that to relate the infinite volume limit to the finite box, that the infinite volume limit 2-point function is larger. So that's also used also for the squared 2-point function. So so we somehow use it in a crucial way. But okay, I mean, you can derive some statement without them, which says that there is a phase transition, I think, but maybe not a nice statement like this one.
Thanks.
Other comments or questions? Okay, so if not, we can thank Marcin again for this beautiful talk.
Thank you very much.
Thank you.